Okay, so hello everyone. My name is Ricardo, and I'm here to present you our work, PAIO, General Portable I/O Optimizations with Minor Application Modifications. This is a joint work with Yusuke Tanimura, José, Haga, Vijay, Chidambaram, José, Pereira, and João, Paulo. So, as we all know, data-centric systems have become an integral part of modern I/O stacks. And good performance for these systems often requires complex storage optimizations, such as I/O schedulers, caches, tiering, and replication. However, we believe that currently optimizations are implemented in a suboptimal manner. And in this paper, we argue that there is a better way to implement them. So, to present you these arguments, let's consider a simple I/O stack made of an application, a key value store, and a file system. So the first challenge is that optimizations are tightly coupled. So they are designed for a specific purpose and a single data-centric system. And to better understand this, let's give it away with a single example. So Silk proposed an I/O scheduler that reduces the latency spikes in RocksDB. And in summary, it controls interference between foreground and background tasks. However, in order to do this, Silk requires changing several core modules of RocksDB, such as background operation handlers, internal queuing logic, and thread pools. So, as you can see, to implement a Silk control algorithm, we need to have a deep understanding of the system's internal operation model and a profound system refactoring. And porting the Silk I/O algorithm to other systems can be a little bit difficult. So what we can do is that we can probably decouple optimizations. So I/O optimizations can be disaggregated from the internal system logic and move them to a dedicated I/O layer. So in this way, these optimizations become generally applicable and portable across different storage scenarios. However, when we do this, we are probably raising another challenge. So by decoupling optimizations, we may lose granularity and internal application knowledge of which the applications were actually implemented. So because layers communicate through rigid interfaces, such as POSIX, we may discard information that could be used to classify, differentiate, and enforce requests at different levels of granularity, right? So, considering again our I/O stack, as you know, key value stores can submit operations from different sources, including foreground, compaction, and flush flows. But at the file system level, it only perceives POSIX operations, such as reads and writes, and it doesn't actually know to identify the origin of these requests. So one of the things that we can probably be interesting to do is that we can propagate this type of information, where application level information that is only known to the application itself can be propagated throughout the I/O layers. And then decoupled optimizations can provide the same level of control and performance as system-specific optimizations. So in order to address these challenges, we propose PAIO. PAIO is a user-level framework that allows system designers to build portable and generally applicable I/O optimizations. So PAIO levers from the ideas of software-defined storage, where we decouple the policies from the actual mechanisms that implement these optimizations. So in this case, optimizations are implemented outside applications as data plane stages. And each of these stages is then controlled through a control plane, where the control plane has global visibility and coordinates all stages or the access to the storage resources. PAIO also enables the propagation of application-level information through context propagation. Context propagation is a commonly used technique on distributed systems monitoring for propagating different contexts throughout the I/O stack in a distributed and local manner. And from our experiments, porting I/O layers to use the optimizations implemented in PAIO require none to minor code changes. So let's delve into the PAIO design. So PAIO is provided as a user-level library that can sit between two I/O layers. And for this, let's consider layer 1 and layer 2, application 1 and the file system, for example. So PAIO can sit between them. But if we want to actually propagate information across the different layers of the I/O stack, we can put PAIO within the application itself. And then this requires some code changes, but as you will see throughout our presentation, they are minor. So each data plane stage of PAIO acts as a dedicated I/O layer and provides different modules. First, it differentiates requests, which allows to classify and provide different levels of granularity. Then we have an I/O enforcement module that provides channels, which are basically a structure through a request flow, and enforcement objects. Enforcement objects are the actual I/O mechanisms that will be implemented over requests, such as rate limiters, compression and encryption schemes, caches, and more. Then we have a final module that is the control interface. So basically, PAIO connects to an external control plane that has global visibility and orchestrates all of the data plane stages all together. So to better understand each of these models in detail, let's consider again our previous I/O stack made of the application, now RocksDB instead of a generic value store and a file system, and a PAIO data plane stage. And also consider the following policy that we want to enforce. Limit the rate of RocksDB flush operations to X megabytes per second. So in order to do this, because PAIO sits between two I/O layers, in this case RocksDB and the file system, it only receives POSIX requests. So we need to actually identify the origin of each POSIX operation, and for that we need to instrument the RocksDB critical path where these operations are actually created. So the foreground, compaction, and flush flows. After instrumenting them, we actually learn from the context propagation part and pass this information to the PAIO data plane stage. For all of the requests that are submitted through RocksDB, PAIO will intercept them and create for each of them a context object which couples the metadata classifiers of each request, including the workflow ID, the operation type, request, the operation context, and more. And then forward it with the I/O request itself to inside the PAIO stage. So at the stage, we now need to actually differentiate and classify each request. So for this, we created two components, one for handling flush operations and another for handling foreground and compactions, which are the remainder flows of RocksDB. And after we leverage from the context metadata object that was previously created, and we differentiate these requests in this way. After differentiating the requests, they will be submitted to a dedicated channel that will handle them. At each channel, requests are enqueued at a submission queue and will then be picked up by the enforcement object. So for flush operations, we have a dynamic rate limiter enforcement object, which implements basically a token bucket that handles the burstiness of flush operations. And foreground and compactions of operations are submitted to a second channel that has an op enforcement object that simply bypasses all the I/O. After enforcing these requests, they are again submitted to return to the original I/O path and are submitted to the file system. Throughout the execution, PAIO is continuously communicating with a control plane through a control interface that basically allows to submit different things. First, the control plane submits housekeeping rules that allows to actually create channels and enforcement objects. Then we need to actually select and classify all I/O requests, and for this we use differentiation rules. And at execution time, because we need to comply with the policies that were previously defined, the control plane continually submits enforcement rules to change any variables that we may need. Also, the control plane continuously collects statistics for the control algorithm that follows a feedback control loop to actually enforce new rules and ensure the policies are always met. So, to understand the feasibility of using PAIO, we conduct several use cases on our paper, but let's focus on how can we ensure latency control in log structure merge tricky value stores. So for this, we consider RocksDB, which is known to have some interference between foreground and background operations, and they generate high latency spikes. So latency spikes in this case occur because flushes cannot proceed, either because low-level compactions or flushes are slow or are on hold. So to address this problem, Silk proposes an I/O scheduler, which allocates bandwidth for internal operations, prioritizes flushes and low-level compactions, and also preempts high-level compactions with low-level ones. However, to implement this, Silk requires changing several core modules of RocksDB and can target thousands of lines of code. So we implemented the PAIO data plane stage that provides the I/O mechanisms for prioritizing and rate limiting background flows. So in this case, integrating the data plane stage within RocksDB only required adding 85 lines of code, of which half of them were for achieving the context propagation part. We also implemented the Silk I/O algorithm in our control plane. And for this, we can actually allocate the bandwidth for internal operations and prioritize flush and low-level compactions. However, because we are agnostic of RocksDB internals, we don't actually want to modify RocksDB, we are not able to preempt high-level compactions. But in this use case, our focus is to demonstrate that by propagating application-level information to the data plane stage, PAIO can actually enable similar I/O control and performance as Silk, a system-specific optimization. So for this use case, we use workloads made of bursty clients, which follow a peaks and valleys kind of distribution, with an initial value of 5 minutes that submits operations at 5,000 operations per second, followed by cyclic peaks and valleys at 20,000 operations per second, 5,000 operations per second. So in the first workload, we conducted a mixture one with 15% reads and writes, and RocksDB experiences high throughput variability due to constant flushes and compactions. And on the tail latency side, we have high latency spikes that range between 3 and 15 milliseconds, and this can go up to 25 milliseconds as well. Silk, on the other hand, due to its I/O algorithm, I/O scheduler, sorry, they actually can achieve low tail latency throughout the entire execution, never exceeding the 5 milliseconds mark. However, Silk suffers some periodic throughput drops due to accumulated backlog. PAIO, on the other hand, follows the same tail latency curve as Silk, and throughout the entire execution, the tail latency is sustained and never exceeds the 6 milliseconds mark. And on the throughput side, because it is actually inspired on the I/O schedule of Silk, it also has some periodic throughput drops due to accumulated backlog. On a read-heavy workload, RocksDB experienced temporary performance degradation due to accumulated backlog, but after the 500 seconds mark, since there is no more backlog to do, it achieves sustained latency performance. Silk, on the other hand, achieves low latency throughout the entire execution, but after the 400 seconds mark, it preempts high-level compactions and is able to achieve tail latencies between 1 and 2 milliseconds. PAIO follows the same tail latency curve as Silk, and it is sustained throughout the entire execution. However, because we are not able to preempt compactions, because we are agnostic of RocksDB internals, it achieves a slightly higher latency than Silk, ranging between 1 and 1.5 milliseconds, an additional 1 and 1.5 milliseconds. For the write-heavy workload, RocksDB experiences high throughput variability due to a large backlog of background tasks, both flushes and low-level compactions. And for the high latencies, for the latency, we actually experience high latency spikes throughout the entire execution. Silk, on the other hand, again, it pauses high-level compactions and only serves high-priority operations, so flushes and low-level compactions, and allows to achieve sustained latency performance throughout the entire execution. However, once again, it suffers some periodic throughput drops due to constant flushes being executed. PAIO, for tail latency, it can actually provide the same latency curve as Silk, but for the throughput, we have some issues. So in this workload, since flushes occur more frequently, PAIO slows down high-level compactions more aggressively, and in this case, it temporarily halts low-level ones. So from this, PAIO experienced a severe throughput drop throughout the entire execution, and this might be resolved through having the actual preemption of high-level compactions to low-level ones. So in summary, we present PAIO, a user-level framework that enables building custom-made data plane stages, which combine ideas from software-defined storage and context propagation. And this way, we are re-implementing I/O optimizations by decoupling them to a dedicated I/O layer. We have built different data plane stages, one that I actually presented in this talk for latency control in LSM-based key value stores. And we also built another one to actually handle per application bandwidth control in shared storage settings, where we have multiple TensorFlow instances sharing the same storage device, and we can ensure the same guarantees without compromising, without changing any lines of code. Finally, on our paper, you can find more results from our experiments, more detail about the data plan stage built with PAIO, and you can check PAIO on GitHub or at dsrslab-PAIO. And with this, I conclude my presentation, and I will take no questions. Thanks.